Hi, everyone. Can you hear me? Hear me okay? Thanks for the invitation to come out. Thanks for showing up on Saturday morning. I appreciate it, and I'm very flattered. And so I'm going to talk about fundamental science with polyatomic molecules, mostly precision measurement, but also some things that are not necessarily precision measurement related that we're doing at Caltech. And maybe some of the big questions that motivate what we do are, can we design molecules tailored to specific science and engineering goals? So this is a recurring theme that a lot of people have talked about here, and I also will as well. Can we find new ingredients to design these molecules? So not just doing the experiments with them, but can we just sort of come up with new tools? But in particular, what we're very interested in is leveraging the unique degrees of freedom only available in polyatomic species. And so in my group, experimentally and theoretically, most of these we haven't worked with experimentally, but we're trying to help put together a toolbox to do all sorts of different science things. So different metals give you different options for optical controls, fundamental symmetry violation sensitivity, laser cooling, but also different features like different spin multiplicities or hyperfine couplings or magnetic sensitivities. And then attaching some ligand to it, you get even more options like high polarizability, tunable electromagnetic field sensitivity. You can scale energies, change energy scales in the problem, get different symmetries, come up with linkers that let you stitch together multiple, say, metals or ligands. And you can also ionize these to open up different options for trapping and control and measurement techniques. So we're broadly interested in what can we build with this toolbox, but also what else can we add to it. So the first thing, what can we do with it? One of the things that you can do with it is look for symmetry violation at low energies. For example, particle electric dipole moments, which violate a number of fundamental symmetries. One relevant one being CP violation, charge parity violation. That's an interesting symmetry violation because it's the same symmetry violation that you need to come up with new sources of to explain why the universe is full of matter and essentially has no antimatter. And there's a deep connection between the existence of electric dipole moments in fundamental particles like electrons, or even composite things like neutrons or nuclei. The alignment of a spin and a dipole moment violates parity and time reversal symmetry. So for example, you can see the parity connection by just looking at a spinning dipole in a mirror, and the mirror image of that particle will have the same spin but opposite dipole moment. But we know that that particle, if this was a fundamental particle, that couldn't exist because these two would be distinguishable. So these moments can only exist in the presence of fundamental symmetry violations. And can only arise due to either new or very interesting fundamental physics. For example, new high energy particles or forces that couple to the electron in a CP violating manner. But we can probe this physics in a low energy tabletop setting using precision measurements. There are three observables that we're most interested in that show up in atoms and molecules that violate these symmetries. There's the electric dipole moment of the electron. But then there are two nuclear moments, nuclear magnetic quadrupole moments and nuclear shift moments. The electron ADM is only sensitive to things that couple to the electron. The nuclear moments are sensitive to things that couple in the nucleus, like to quarks or to pions or the strong force. They're all enhanced in heavy species. And these nuclear effects are enhanced in deformed nuclei, either with a quadrupole or an octupole deformation. But the methods that you use to look for these generally are very similar. Like people usually just call all of these EDM experiments because the way they proceed is almost identical. But they have very complementary science reach in terms of looking at sort of leptonic versus hadronic symmetry violations. And as a motivating example, which we've been, in this community, we've been showing this example or a similar example for a really long time. And I think when we first started showing it, it was like, maybe one day we could do this. But now I think this is the kind of thing that I think hopefully a lot of people are convinced you really could do an experiment like this. Not right away, But again, as a motivating example, say you had 1,000,000 molecules with 100-second coherence time in a heavy deformed nucleus, and you had good quantum control and error, robust error rejection, and you integrated for just 2 weeks, you'd be accessing 1,000 TeV scale CP violating physics in both the hadronic and the leptonic sectors. So very, very broad coverage. And this is well beyond the reach of even conceivable future accelerators. So not just the LHC, but even sort of anything you could think of. So this is pretty exciting. Of course, the first generation of experiments won't have these numbers, but I think none of these seem ridiculous at this point. And then even after this experiment, even more speculative future things like quantum enhanced metrology or highly exotic nuclei could continue to give even more enhancements. So there's a lot of room to go with this approach. So if you want to find a molecule to do an experiment like this, what do you need? You have some needs. One is you need a heavy nucleus to get these big enhancements, the heavy nuclear enhancements for both the electron and the nuclear stuff. Both need this. They also both need core penetrating electrons for very different reasons, but you need basically lots of either S or P content at the nucleus. So, and that's good news for a laser cooling molecules approach, because these structure requirements are compatible with these alkaline earth-like based laser coolable molecules. So if you take a heavy metal like strontium, barium, ytterbium, radium, and you stick something to it like fluorine or something that bonds like fluorine, with this story you've heard about a few times now, you get a molecule which is laser coolable, as you've heard, but also because the CP violation sensitivity comes from the electronic structure, that's also generally unchanged. And this has now been shown for a very wide range of different species. So you can combine laser cooling and ultra cold techniques with this CP violation sensitivity. There's one thing which this recipe, just sort of as shown, is maybe not as good news, is that this electronic structure does not give you parity doublets. So these all have, at least for this recipe, you get a doublet sigma structure. There's no omega, there's no lambda, there's no doublets like that. It's just a rigid rotor rotational structure. If you don't know about parity doublets, that simply means that you have a structure where each rotational level is split into a closely spaced doublet of opposite parity. Closely spaced meaning they're typically below like 100 megahertz, sometimes much smaller than that. And they have a lot of advantages, both in general, but for these experiments in particular. You get high polarization in small fields, but you can also do a trick called internal comagnetometers, where you can just flip the molecular dipole just by addressing one or other sort of Stark-aligned state with your laser, and that flips your CP violating signal without actually changing any external fields, which is a really big boost for systematic robustness. And as has been alluded to previously, this parity doublets generically require some mechanical angular momentum, meaning that it's like sensitive to parity, so not like a spin, with a projection along the internuclear axis. And then the doublet arises as superpositions of opposite orientations of this projection. So for example, in a diatomic, the electronic angular momentum can have a projection going this way or this way, and that gives rise to your doublet. And in diatomics, that's the only option, because the rotation is necessarily perpendicular to the internuclear axis. So the only other mechanical angular momentum, orbital angular momentum, that will give you this projection is from an electronic angular momentum. And these doublet sigma states don't have any. And you can make fairly general arguments that it would be hard to find a heavy, laser coolable, neutral, non-sigma molecule, diatomic. But in polyatomics, they always have features like this due to the fact that they have lower symmetry. So there are always mechanical modes that have angular momentum around a symmetry axis. So L doubling, where the vibration mode where the middle nucleus is orbiting around the symmetry axis, or K doubling, where you have like rigid body rotations around the symmetry axis. You always get those, and that's independent of the electronic structure, say, of some metal here. And so symmetry, so that's a nice platform for symmetry violation. So you can get EDM sensitivity and nuclear sensitivity and laser cool ability from your metal, and then from your ligand you can get high polarizability and parity doublets. So it's a way to combine both of these. In this case, so more complex ligands would give you even more advantages than, say, OH, something like a symmetric top or an asymmetric top, but they're more complicated. So the OHs are a good starting point. And the things that are, the molecules that are sort of relevant for what I'll be talking about are CaOH, SROH, and YBOH. They all kind of look very, very similar. They have a science state, which is a bending, metastable bending mode, but with a fairly long lifetime of several hundred milliseconds or so. So at Caltech, one of the things we're doing is building a nuclear magnetic quadrupole moment search using an odd isotope of ytterbium, which has a large quadrupole deformation. The first generation experiment will be a buffer gas beam experiment, so spin precession in a beam, but with the option of adding laser cooling and trapping in future generations, although this molecule, for a number of reasons, would be very hard, very challenging to laser cool. You could laser cool it, but we're not gonna do that right away. So some of the things that we've done along these lines experimentally, we make the molecules through a chemical production process in our cryogenic molecular source. We're using a CBGB, that's our cryogenic beam source. We vaporize some mixture of ytterbium and chemically stable ytterbium trihydroxide, and then we excite. There's a lot of just atomic ytterbium created in this ablation. If we drive this intercombination line very hard, this ytterbium reacts with ablation products to give us more YBOH. So just by shining in this light, we can get roughly a 10-fold or so enhancement in our molecule production, because this excited ytterbium metastable state has enough energy to overcome the reaction barrier that the ground state can't overcome to react. So we get a lot more molecules, but there are also some other nice features of this. One is it actually puts quite a bit of population in vibrationally excited states, but then rotationally and translationally cools them, because the vibrational quenching is very inefficient. And this is a useful trick for a few reasons that I'll talk about. Another trick you can play is you can use it as a feature to do spectral assignments when you have very dense and congested spectra. So for example, 173 YBOH has isotopic rotation and ytterbium hyperfine structure that's all about the same size and all overlapping. So if you look at a spectrum, this looks like those big molecules you saw yesterday, except this is like a triatomic, but there's just so much going on that it's the spectrum is very messy. But by playing some tricks with the chemical production, you can isolate without modeling just the 173 spectrum that you're interested in, and then fit to it. And so it means that you can basically extract like this data out of this spectrum sort of directly, which is really handy and was important for the spectroscopy of this molecule. Once you have the spectroscopy of the molecule in the ground and excited states, you can come up with a photon cycling scheme. You heard a bit about this the other day. Ytterbium, the 173 ytterbium has a 5/2 nuclear spin, so it has large, and ytterbium has a large quadrupole moment, which is why we like it, but that means that it has a large, like regular electric quadrupole moment and a big Fermi contact. So it gives a very complicated spectrum with a lot of levels. But you can find rotationally closed cycling schemes that basically plug all these different hyperfine channels, and in particular you can find a scheme where you can address all of the ground states with just one laser that you modulate with 2 EOMs that works in the sense that it addresses every ground state is addressed by one of these two combs. But also it avoids unwanted regions. That's something you have to be very careful about in a molecule like this, where the spectrum is so dense. If you just say let's just drive these lines, you're probably going to drive other lines out of some other state into some other state, other excited state that's going to get leakage. So you have to be very careful with that to find like isolated regions. But here's a scheme that works, that hits all these lines, avoids these sort of bad regions that give leakage, and we can do this in the lab and show that it works. With just these one laser and 2 EOMs, and we can show that we can get, with no repumping, we can get about 9 photons which is exactly what you'd expect from the Frank-Condon factors in this molecule. We predict that there's sort of a percent-ish scale leakage due to n equals down to n equals 3 in the ground state, due to some excited state sort of hyperfine coupling weirdness. We haven't been able to see it just because this is sort of too small to observe without any vibrational repumping. But it's something to keep in mind. We also worked this out and showed it for 171 YBOH, and we're putting this together to share. We also have been looking at this science state, so this metastable bending mode where we would do the measurement. We studied it by driving an off-diagonal transition to the non-vibrating excited electronic state and then collecting the fluorescence. And so we measured about like 35 lines in the lowest 4 or so rotational levels so we can get all the constants to about 1 megahertz in this state. A challenge with this is because this is you heard some discussion about this yesterday, this is a forbidden transition. It violates a delta angular momentum. You can't change the vibrational angular momentum by 1 when you drive an electronic transition. So it's a forbidden transition. It's very weak, and we can still see it, but you can't look up what the shape should be, which is normally what we do when we're assigning a spectrum. You just look up, like, what does the spectrum look like in a similar molecule? But you can't do that with this one. By the way, if you were paying attention to Land's tables, this was measured. This branching ratio was measured at Harvard. It's very small, but not 0. The transition occurs via vibronic and spin orbit perturbations, exactly like Land was talking about yesterday. And so we implemented a model like that, including the sort of the full sort of rotational and fine and hyperfine structure, and can model this spectrum pretty well. We also we mapped out the Stark and Zeeman effect. They behave sort of exactly as we predicted, which is good. It's complicated because of the angular momentum coupling, but there weren't any surprises, which we were happy about. The dipole moment's about 2 dBi. You can see that you get sort of 50%. We get about 50%-ish polarization in small fields of like 100 volts per centimeter. So that's good. The Zeeman effect is consistent with just the electron spin, giving all the magnetic G factor. So we're writing this up. We also did this for the odd isotopologues, including the one we're interested in for the MQM. All these bending modes should look basically more or less exactly like this. We also worked on some tools to map out repumping transitions at high resolution. That can be challenging because typically the way you do that is you sort of add your first laser, let the population build up in some excited state, then put another laser, and then just keep doing that. But that needs a lot of lasers. So we, and you heard something similar yesterday with barium fluoride. So we combine the fact that we get sort of quite a bit of excited vibrational population due to this chemical enhancement thing. And then we implemented a very sensitive FM absorption method, so we could measure sort of with pretty high signal to noise. We could measure say like the V equals 3 directly, just without any pumping or cycling or anything. Just see it in a direct absorption, and you could play some tricks to push the sensitivity even higher to see basically all the repumps that you'd need just directly with one laser, and you get all the molecular constants to about 1 megahertz or so. And so this is a fairly generally applicable method that should be make it hopefully easier to map out all of these repumping transitions in a variety of species. So we've mostly been doing spectroscopy so far because molecules are complicated, but ultimately we want to do like a CP violation measurement. So we've been starting to more and more do things toward that end, like starting to work with spin precession in our YBOH beam, optical pumping into the science state to get even more population there, instead of just relying on this like chemical enhancement, which is what we've been doing so far. and then starting to like build the science chamber, like the chamber and the shields and the fluorescence collection and that sort of stuff. We also work on poly-EDM, an electron EDM search in laser-cooled and trapped SROH. This is a collaboration between myself, John Doyle, Tim Steinley, and Amar Vutha. Zach is going to talk about this next, so I'm not going to say anything more about it. But also just remind you that Loic talked about this EDM Pathfinder with CaOH, where we basically did like a mini EDM experiment with CaOH, showing that like all of these things that we would hope worked like actually do work in a species with identical structure. So that's encouraging for us. So a theoretical direction that we're interested in, which I'll now shift gears to, is new structures for optical control. And one example that I'll talk about is, well, I guess first I'll motivate generally. What do I mean? So there's this picture, which we've seen a number of times now, which is sort of based on this, general principles to making like cycling centers and molecules, which works very, very well. So doing something like, calcium or strontium or something with something that bonds like F, and you get this polarization of the wave function away from the bond. This works very well. But a question that we're interested in is, are there other approaches? Like, can you find other types of metals, other types of bonds that give you a structure maybe not like this, but allows you to cycle photons? And so one question you can ask, which someone did ask yesterday, is can you come up with cycling centers that have more than one valence electron? So instead of calcium, something like aluminum or silicon or phosphorus or something that would have multiple valence electrons. Those are interesting maybe because they have narrow transitions, metastable states, non-magnetic states. It opens up more of the periodic table, so more nuclei, more chemistry, more precision measurement. The real reason that we were interested in is just like the fundamental question, like, can you find them? And it's an interesting question because the previous recipe fails. So you heard, aluminum fluoride and aluminum chloride are great. They have two valence electrons. They cycle photons very, very well. And so you could say, does AlOH work? And the answer is no. It's terrible. The bond is too covalent. So the molecule just flops like crazy, and you don't get any diagonality. If you make this bond more ionic, it doesn't help. So you have to do something else. So here's something that works. It turns out if you make the bond more covalent, you can get cycling centers. And the hand wavy argument is that if you replace oxygen with sulfur, which is bigger than oxygen, the aluminum and hydrogen, say for if instead of AlOH you look at AlSH, the aluminum and hydrogen distances increase, and that so their repulsion goes down, and so it allows them to sort of lock into what you would naively expect as like the 90-degree perpendicular bonding orbitals. And this happens, for example, H2S is very close to 90 degrees, whereas water is very famously not 90 degrees. And it's sort of this mechanism is what's going on. And so you get, in some sense, you stabilize the geometry of the molecule, which is what you want for Frank-Condon factors, through this sort of like kind of geometrical reason. So it's sort of different from relying on like an atom-like structure. It's more like you're using the geometry of the entire molecule. And in this paper, we explore a little bit that it works for heavier metals. It works for higher valence things, like things with 3 or even 4 electrons centered here. Some preliminary work that we've done suggests that this might work as sort of a general linker paradigm for attaching to something like benzene, but with a very different structure. So yeah, this wasn't we didn't just hand wave. We did like proper ab initio calculations. If you saw Pavel's talk yesterday, those are exactly the tools that we use, with a lot of help from Pavel and Anna's group. So we used like these EOM-CC methods. And the cycling, for ALSH, for example, and the similar ones, the cycling transition is from this ground state to, in particular, this out-of-plane excited state triplet. And that's important for this sort of decoupling of the bond angle and the electronic state. But that also presents some challenges, especially for photon cycling, but mainly for laser cooling. It would, for photon cycling, this is fine. For laser cooling, there would be challenges, which is this transition. It's a forbidden transition. It's a singlet triplet transition, so it's weak. Also, this in-plane triplet is in the middle, so you have like an intermediate leakage pathway. Although, if you've been paying attention, those are maybe not so bad if you have a positive attitude. You can maybe even use them for stuff. But also, you can make both of these problems get much better if you go to heavier metals. For example, like indium SH, spin-orbit mixing makes this line a lot stronger, and it pushes the energy levels around so that these sort of bad leakage channels get weaker. So that's maybe interesting. So other theoretical directions that we've been looking at are also similarly like higher bond order. So it can find like generic recipes to make non-single bonded things. And the answer is it looks like it. So that's something that I didn't talk about as much because we're not like done figuring that out, but we think we figured it out. Stitching together multiple cycling centers with carbon-carbon triple bonded ligands, which also works, gives you sort of two quasi-independent cycling centers, although with some caveats. And also coming up with ligands that you can attach to a heavy nucleus and then ionize, and tuning the ligand to give you different experimental options. So this is something that we're doing in collaboration with Andrew J.'s lab at UC Santa Barbara, where he's actually made these molecules with radium. You'll hear something else about heavy, interesting radioactive molecular ions later today. And thanks to my group, I needed a photo. This one's old, but thanks a lot to our collaborators, especially the theorists who helped us pretend to be theorists during COVID when we couldn't go in the lab. So, thank you. I think they probably would, and that's an important caveat that we always put in the papers, is that and that's something important to keep in mind, is that a lot of the stuff that Lan was talking about yesterday and Jinjun, these higher order like vibronic things, can show up on the 10 to the minus 4, 10 to the minus 5 level. That's a number that's relevant for laser cooling, and that's something we did not look at those. Those would definitely need further investigation to see to what extent those would show up, and they almost certainly would. I mean, they're polyatomics. They're going to have there's no reason they're not going to have those. Yeah. Yeah, the statistical. It's always I like to quote it in terms of like the underlying observable, especially for MQMs, because the actual units are some nonsense. But we're with the first generation apparatus, meaning the one we have now with like no improvements. We think that we can make the most sensitive measurement of an MQM in like a few minutes, but then if you relate that to like, okay, that's a little unfair. I should just stop there because that sounds really great. But it's a little unfair because if you then try to relate it to the underlying observables, then it would be more like sort of a few days, like sort of 2 weeks, several days to 2 weeks to kind of get to a range where you're starting to probe, get to the limits of the underlying physical sources. And there are some things that we would know to do for like a generation 1.5, like easy things like, rotational pumping or, putting in a really corny magnetic, little magnetic lens or something that would push that number up. We might do some of those things, but I think for that number, we're not assuming that we're doing anything like that. And then there's of course laser cooling and stuff, but that's.
Thanks, Nick. Great talk. I also like your orange beanbox.
Haha, thank you. Caltech Orange.
So there were extra peaks in your 174 YBLA spectrum.
Right.
You marked with the asterisk.
Right. Yeah. My thing just stopped working. Okay. Let's do it the old-fashioned way. So we figure, so those are just simply unassigned lines, and we're pretty sure that they're either different isotopes or more likely overlapping bands, because there are a few other bands in this region that aren't fully unknown, including like up to vibronically non-trivial excited electronic states. So that's what we're pretty sure they are. Yeah, and in these sort of messy molecules, there are always the asterisk above the peak thing is pretty common. Yeah.
Okay, final question. Thank you, Nick, for a great talk. You mentioned 100 seconds is ideal for this time.
Mm-hmm.
On the first slide, your lifetime was about 700 milliseconds. Right?
Ah, yeah.
I was wondering how.
You caught me. But no, you didn't, because look what I put in there. So this is for this slide, for exactly no one's ever called me out on that. So thank you for noticing. But yeah, so here I put, for example, something that is not linear. So like a symmetric top or an asymmetric top, the lifetimes of these states are essentially rotationally excited states, often with some symmetry protection to prevent their decay to the ground state. So it's weak transitions at relatively low energies, so the lifetimes of those states are very, very long. So in that case, you'd be limited by something else in terms of lifetime instead of radius. So 100 seconds would still be very, very hard, but probably doable.
Okay, let's thank Nick again.